Hi everyone. How are we doing, meet.js? Okay, cool. So the title is a little bit of a mouthful, but hopefully we're gonna break it down little by little and make it easier to understand. So today we'll be talking about serializing data in TypeScript via binary protocols in a way that's hopefully faster than the current alternatives. And we're gonna see what are the problems with the status quo. So thanks again to the meet.js organizers for inviting me here in Wrocław. I hope I pronounced the name of the city right. And as you would have guessed by now, I'm not Polish at all. But before introducing myself, I will encourage you to point your phones to that QR code so you can save the slides for later. So I am Alberto Schiabel. I come from Venice, Italy. I'm a software engineer. I've been doing that for around 8 years. I work with Prisma.io, which is also one of the sponsors tonight. We're trying to innovate the landscape of database access tools, especially for TypeScript with type-safe practices, and kind of evolve in that area. But I'm also like a contractor for some other projects, and I also gave workshops and conferences at companies. So let's keep in touch. And turns out that with Prisma, we're working a lot with interacting between Rust and TypeScript, because that's what our code base kind of consists of, and using WebAssembly. And while today we're not going to talk about WebAssembly, we'll touch on some points that would be useful for that use case. So first of all, how do you usually transfer data from one service written in one language to another? Probably with a REST API, but that's already a big question, so let's break it down and make it simpler. How can we do that between two TypeScript services? Well, usually, we have something like that, right? We have a client and a server. The client submits a request, the server replies, and usually the medium by which they communicate is, of course, over the network via HTTP, but the data itself is encoded in JSON. So we have a serialization of some data coming from the client-side memory. It's transformed into JSON, fed to the server, returned back, and the result is well likely another JSON. So you probably have some code like that, where you have a client contacting a server. You can have like an Fastify endpoint, an Express endpoint. What you will do is, you will just perform a fetch request, and you're gonna stringify whatever input you have, and then you're gonna decode, you're gonna call JSON.parse on the input, and maybe your Fastify or Express framework will do that for you. You're gonna use that to write to the database, perhaps, and then you're gonna return the result back to the user. And the client is just gonna call await response.json. So that's all fun and games until it's not, because JSON has a bunch of problems. So first of all, ambiguity. Let's say an example here. We have a very well-named object. You see 3 properties, A, B, and C, and we have a bunch of data. And at first glance, maybe you're ready to tell what the data represents, but your computer isn't. It has to go through every byte of it to understand what it is. So let's start with the first one. There will be the first series of numbers from the pi. And turns out it's encoded as a string. So what do we want to do with that? Is that a big int, because technically it fits, or is that a string? What about this? Is that ISO something date, or is that just a normal string that we want to store somewhere? How do we want to treat that data? And what about this? Is it a list of lists, or is it the input parameter for a map object in JavaScript? Turns out we really don't know. JSON is described as a self-describing language, because basically the syntax you use to represent the different data types it supports already tells you what kind of data type it is. You have quotes or you don't, mostly, and then you have the booleans. But it's not self-describing at all for our purposes. So the sender and the receiver, they need to understand, they need to agree, hey, we have this value here. How do we want to represent that? What kind of entity does it represent? What kind of actions do we want to perform with that item? So some clever folks came up with the idea of annotating JSON objects. Like they add a schema on top, for instance at blitz.js with super JSON. So we have the first property from before, and actually they turn it into something like that, where you have the JSON content, and you have some metadata that tells you, hey, that property actually is a big int. So when you deserialize that, that should become a big int. And by the way, if you try to encode a big int in pure JSON, or even a data for that matter, you're gonna get some errors, and they can be hard to parse. So it turns out it was big int all along, and that's what we wanted. What's the next problem? Type safety. JSON is not type safe at all. This is similar from before, right? We have a user type. We retrieve data from a fetch request. We get the request from .json, and we cast it. We assume it's a user. What if it's not? What if the server somehow got a bad commit, and we are receiving data that is not in line with the type we have set at the top? So please do not do that. There are some alternatives. Like, you don't really want to validate. You want to parse. Why is that? Because with validation rules, you were always gonna forget some of them. And technically, they don't really make sense if you reason about that. There's a beautiful article. I invite you to read it later. And some folks really took that seriously. So how many of you know the Zod library for TypeScript? OK, that's plenty. How many of you know TRPC? OK, that's basically what they're doing. So great that you're using that. Problem, JSON has some extra memory allocations. And especially in cases where memory is constrained, and you're all used to AWS Lambda with maybe gigabytes of RAM, but what about Cloudflare Workers or Dino Deploy or like similar platforms where you have a bunch of megabytes and that's it? So you need to think about that. Usually you get a JSON string, and when you need to encode it, you have to allocate extra memory on the heap, so like the dynamically allocated memory. And you need to do that even if you need to access only a very small tree of your JSON, a very small portion of it. You first have to allocate a bunch of memory, parse it all, so make sure everything is valid JSON, and then retrieve data. There are some alternatives like JQ on the CLI. Turns out they still allocate more than they should. So we kind of have the same limitations in JSON that you will find in other text-based protocols. And that kind of brings us to the question, what is a text protocol? So let's clarify this. First of all, serialization. Serialization is essentially, you take some data representation you have in memory in your programming language that you can play with in the console, for instance, and you represent it in a way that is compatible with network transfer, storage on disk, etc., so that you can transmit it to some other computer or device. And this format usually used for serialization is either textual, like JSON, or binary. And that's usually architecture independent. And the serialization is just the complementary operation. So you just take serialized data, and you turn it back into its original in-memory representation, so you can play with it. Not necessarily original in the case in which you are transmitting among two different languages. And really, what you have to think about when it comes to serialization and deserialization is packaging things, as you will kind of giving a gift to your friend. You buy a Nintendo Switch or something that was sold here before. You package it so that your friend doesn't know what it has. Maybe you put some other info. You put a ticket or a greeting for your friend, and then your friend is gonna open it and put it on their home devices, etc. So that would be like the deserialization part. And a little bit of reminder also from Computer Science 101, endianness. It takes pushing bytes over the web can be more difficult than expected, because not every machine agrees on how these bytes should be ordered. So it turns out there are two big mechanisms. One is big endian, where you basically put the most significant bit always first, and little endian, which most of your devices probably use, where you put the least significant bit first, byte first, sorry. And the protocols, turns out they need to agree on this as well. So a little bit of an example. Take the current year encoded as a string, and we explore. Can you still hear me? Yeah. And you explore like the binary representation of it. If you now use XXD, that's just a binary reader. It shows you in the left side just the line code in hexadecimal. On the right side, it shows you the textual equivalent if the bytes, the equivalent bytes are textually representable. Otherwise, it just shows you a dot. And in the middle, there are like the groups of bytes it's going to read. So you see 32 matches, the hexadecimal for 32 matches the 2 string, the hexadecimal for 30 matches the 0 string, and the hexadecimal for 33 matches the 3rd string. It's a little bit of tricky. You probably have to draw lines around, and we did that, but later. OK, I think yeah. So protocols. Turns out that a serialization format isn't enough to describe everything goes on, and the other thing you need is some sort of agreement on the meaning of everything you have encoded. So basically, it boils down to understanding the semantics and defining the semantics, the semantical interpretation of the data you have transmitted. And usually, you do so by writing a specification that involves a schema. Textual protocol. We've already seen examples before. Basically, they use bytes that can be converted to either ASCII or UTF-8. JSON is one such example. There's XML, etc. And they use a bunch of conventions so that they can represent data and types within the boundaries of those character bytes only. They require any operation they need to parse strings first. And they tend to be very verbose in terms of data, because, for instance, numbers, they're not represented as numbers. They are represented, they are kind of split down character by character. So rather than storing a 64-bit integer in 64 bits, so 8 bytes, it's stored as 64 characters. On the other hand, you can easily inspect that. So you can open a JSON on your Visual Studio Code, and you can just read that and understand what it contains. This is just an example of how a minified JSON will look like. So without getting into too many details, you see on the right-hand side that some of those bytes there in big endian, they actually say that this is an event. It's called meet.js, and the year is 2023. Binary protocols are actually what we're really interested in today, and basically they use every kind of byte. They're not constrained to textual byte only. So they use non-printable characters as well. And they are far more compact. But of course, parsing them relies on some sort of previous understanding of how the data is laid out and transmitted. So you need to really know the protocol before dealing with any data in binary. Have you ever tried to open a save file from a game? For instance, like from Need for Speed or something like that, you usually have a save file.bin, and that's you need to understand how the game application encodes that in order to modify your stats, and for instance, increase the number of cars you have, the number of money you have, etc. So similarly, this is a binary I just decoded, and you are still able to read meet.js, but you can't really know whatever the rest was originally. And you see all the dots. Those are points you don't really understand without the protocol. So the good part is that we can also support 0 copies. What does it mean? It means that once you have parsed the message, you can perform a bunch of operations, and they do not require any CPU cycles. They don't require any further memory allocations also. And they are primarily relevant when with high-speed networks, because when the network is low, you don't really care about optimizing how fast you're able to decode data. But when you get gigabits and like tens of gigabits per second transmitted from point A to point B, then the data gets shared in almost no time. So if you want to be reactive, you need to be very fast. And there are some examples. Captain Proto, we're going to see a little bit of it, message pack, and Structure. So some examples in TypeScript. So Structure is quite a nice library made by one guy who published a blog post on Medium and then kind of left off. You can install it. It's mostly written for Dino, but you can install it on NPM as well. And it relies on data views. So how many of you have heard of data views before? OK, it's quite of a niche. It's basically a low-level interface that allows you to move and interact with bytes without caring about endianness. And they have like a bunch of very useful methods where you have like set uint 8, and you just put a value for set uint 8, which is like a unsigned integer with 8 bits. And it's basically, they are just an abstraction for our array buffer. They have a bunch of features that are quite relevant. So first of all, they are type safe. They rely on JSON schema for describing the data, and then they allow you to have type inference out of the data you have described. They don't require any compilation, which is a great thing. But also, they provide you with a bunch of, they allow you to store strings as UTF-8. Usually, JavaScript uses something like UTF-16, almost. And they have a standard library for your binary encoded data. So you basically take the data you have from a JSON or whatever, from an initial source. You encode it in data view, and that just lays it out sequentially as bytes in memory. And then you can modify those bytes, and those bytes modify the representation of your data. You can transmit them as they are to another service or whatever. They can just read it with that library. And they're not going to do a parsing. They're just going to take that bytes, put them in a box, and give you access to portion of that box. So you can have basically lazy parsing of just a small field that you're interested in without paying the cost for decoding all the other fields and properties you had around. A little bit on an example. Everything starts with an import view from Structure. You have an event type, name and year. A similar example here. And then we initialize a new view. And the way it works is that we specify a JSON schema. You see there at the top, type object, which can only allow us to have types whose size is known a priori. So for instance, for the strings, strings is a varchar, so we need to tell it how many characters do we expect for that string. In this case, 10. And we also say, well, for instance, this is a number for representing a year, but we don't want to spend 32 bits, just spend it 16. And we use that view object we got, event view. We just call the from method. We pass something like a JavaScript representation that will be your in-memory model of your data. And what you get is a data view, so just an array buffer. And you can have property getters and setters. So it's totally modifiable. You call it get.name. Get name. You get meet.js. You modify the year to increase it by 1, and it's going to modify that in place. And how does it look like? If you run console log on that event view.buffer, you're going to get something like this, a data view. And that array buffer will show you the content as bytes. And if we inspect that with the tool we've seen before, now there's a little bit of arrows. Hopefully, that will make it clearer. So like the first 7 bytes in big endian, they will just be the string meet.js. So there's a one-to-one correspondence. 6D, that's just M. 6.5, that's just E, right? And then we have 3 bytes. Those are empty, 0 bytes. That's called padding. What's that? Well, we allocated 10 bytes, but meet.js is only 7 bytes long. So the difference, we still need to store it somewhere, and that's, by convention, it's always empty, 0. At the end, we have 2024. Yeah, and it's only 2 bytes long rather than 4 because we used that B-type property before. B-type is actually useful for representing dynamically sized objects because we don't really want to deal with strings that are always some characters long, right? So it turns out if we specify B-type map, we can have any kind of string. They look a little bit different in the sense that now they have some sort of string section initializer going on. So they have to mark the end of all your statically initialized data, and from the rest of the data can grow. Some drawbacks also about here. They are always encoded. They always encode a bunch of memory at first, and then you reuse it. But you can't really grow them. So if you need to store data that is longer than they expect, you have to modify that yourself, and you need to know how many bytes you need upfront. And it's not totally compatible with JSON schema. The types you get are not as tight as the type inverse you will get from Zolt, for instance. And objects, the way that they structure objects can be probably improved. But just to give you a quick example of another comparison, very quickly, Cap and Proto. How many of you have heard it? Almost no one. Wow. That's primarily used in Cloudflare, and it's been built by one guy at Google who worked on protobuf too. Maybe you have heard about protobuffers? Okay, a few more people. What's that? Basically protobuffer, but faster, and with a slightly different syntax. And they have a very funny diagram in their homepage where they tell you that they are infinitely faster than protobuf. Why is that? Because the diagram only takes into consideration the parsing and the encoding of data. And since Cap and Proto is 0 copy, they don't have any encoding of data once you initialize that. And you have you model data as rooted trees. They're called messages. And the canonical implementation is in C++. But there are a bunch of other languages supported. So what do I mean by supported? It means that it's kind of up to the open source community. There's one for TypeScript. Turns out it's broken. It's been broken for at least 2 years for a number of reasons. Even TypeScript 4.8 and upfront is no longer supported. ESM, you can't use that. So you can only use that on old Node.js versions, basically. So I took the liberty of forking it, modifying it a little bit, hopefully making it a bit better, although I haven't spent the time I wanted to. And how will it look like? You have a basic schema. I'm not going to spend too much time on the syntax, but it's C-like structures. You need to put an identifier on any field. You need to have a unique identifier at the top. You have a generation step, compilation time. You can pack your data. It also uses array buffers, so very similar to the other one. But when you unpack it, you can observe how it looks like. It uses a bunch of zeros. So that's why they have the packed version. So the packed version is just compressed. What's the problem? You throw 0 copy out of the window. It's 8 times slower in memory. And using just the compression over the network will be better. And I'm going to skip that part, because you're going to find that in the slides. There are pros and cons with each approach. But what I really would like to have is something that gives us the best of both worlds. Something that is actually type safe, something that can support a binary first standard library. Fun fact, Structure supports binary search on binary strings. So something like that is pretty cool. I would like something that is a drop-in replacement for JSON and Super JSON in TRPC, but still allows us to parse things like Zolt. And also allows us to decide how we want to serialize some complex data that are still very useful in our everyday task. So if any of you would like to contribute to that, please reach out. And why did I find that? Well, it turns out I stumbled across problems with data serialization working with WebAssembly. I've talked about that last Node Congress. So if you're interested, please also take a look. And you will find out why I wanted to find an alternative. So that's all from me. You have some sources for later. And you also have a code sandbox to play with Structure online. So thanks for having me.
Thank you. Let's take a seat. We don't have a lot of time, but we also don't have a lot of questions, so that should match. Let's start with this one. So I think someone believed in the Java Summit bit from before, and the question is, doesn't XML solve 2 of the problems you mentioned?
Okay, what will be the
the question was asked early, so at the stage where you were describing problems with JSON and how they're fixed.
Yeah, it describes, it resolves the ambiguity, but it introduces so many other problems that you really don't want to probably deal with that. Like, have you ever tried using XML, I don't know, in React Native, or platforms that don't have like a native XML parser like that? It tends to be very bloated. So also the size, in terms of like, it takes time to parse and to transmit. So no, I wouldn't consider XML as a solution. No.
Yeah, especially parse.
Yeah.
All right. Why not use Rust-based tooling and compile to WASM?
And that's exactly what I did. Like I have a demo, but that will be like prepared for a talk I have in 2 weeks, where I use Cap and Proto for WebAssembly. So it works. I don't think it's as fast as it could be. And again, the problem is with the unpacked representation of message Cap and Proto, you're using more bytes than the equivalent JSON would use. Although most of them are zeros, so you don't really pay too much for it. What's the problem? The Rust compiler, although it's much in a better situation than the TypeScript compiler and a library we've seen before, it's very quirky to work with. And if you use Rust and you take a look at probably about the lifetimes, and if you take a look at how lifetimes are implemented in that library, capnproto-rust, you will realize that it doesn't make it feasible for zero-copy operations. So what you need is like, you have to allocate some memory up front on a so-called writer, like a message writer, and then you can reuse that over the lifecycle of your application. Otherwise, you're gonna pay heap allocations every time, and that kind of goes against the argument we made before.
Yeah. OK. If you try to make it fast, there's one more that I wanted to ask, really. So what's the use case for this that you want people to remember?
OK, so the use case I was presented with was having fast data serialization between Rust and JavaScript. Why is that? Because we're heavily targeting Cloudflare workers and other edge platforms. Turns out they don't have any file system at all. So you can't use the usual FFI bindings you will use to reuse Rust libraries in Node.js or JavaScript or whatever. So either you have to rewrite your Rust logic in JavaScript, which I'd rather really change the job, or you can just convert the Rust to WebAssembly and import it from there. But WebAssembly serialization has its problems. Please just take a look at my previous talk, and you will probably realize what those problems are. But you can also find me around, so I can chat later.